Let's do another example of the graphing strategy to graph a rational function. There's a lot of information going on, so it's good to have more than one example to look at. So the instructions are exactly the same as the previous problem. The main difference here, though, is that very nicely for us, they give us the derivatives. So they give us the original function f of x, they give us f prime, and they give us f double prime. So instead of us having to take the derivative, we can actually really focus on finding the information about the graph. So let's begin with f. The first thing we do is look at the domain. It's a rational function, so it's going to be all real numbers except one makes the denominator 0, and that gives us x is equal to -1, so that's what it cannot be. So in the domain, we have all real numbers except x cannot be -1. You can also write it in interval notation. The x-intercept, we take our function and set it equal to 0. We bring the bottom over. Anything times 0 is 0. We get x is equal to 0. As I've said previously, I personally always like to write it in point form. Then we do our y-intercept. That means that we plug in 0 for x. That will give us 0 at the top, 1 squared at the bottom, which is 1. 0 over non-zero is always 0. So the y-intercept is also 0, 0. A little trick, a little concept. If you have an x-intercept that is 0, 0, the y-intercept has to be 0, 0. Let's move on to the asymptotes. So we always set up the horizontal the same, the limit, as x approaches positive or negative infinity of x over x plus 1 squared. Now in the top, it's easy to see the leading term. Again, I'm using the leading term because x is going to infinity, and that's always how you find the derivative, the limit when you're doing polynomial and rational functions. You look at the leading term. Now in the bottom, it's hard to see what is the leading term because it's factored. So we need to unfactor it. So this tells us that we have 2x plus 1, which would give us x squared plus 2x plus 1. And now I can see that the leading term is x squared. So I have the limit as x goes to positive or negative infinity of x over x squared. I can simplify that because I have a 1x in the top and 2 in the bottom. So I can cancel 1 out. That leaves me with 1 over x. And then in case you don't remember this from a little bit ago, this was a very special limit. It was called the reciprocal limit. If the x is in a fraction and it's in the bottom over a number, a fixed number, and the x is getting really large either in the positive or negative direction, the fraction is getting really small. So it's approaching 0. So as x goes to infinity, y goes to 0. So in a horizontal asymptote, this number is the horizontal asymptote, what you get as a limit. And we have to write it as y equals 0. All right, next we're going to do vertical asymptote, which indirectly also tells us that we have to do in the holes. So that comes from what makes the denominator 0. I only have one number that makes the denominator 0, so I only set up one limit. And because x is approaching a number, our go-to is to plug in. So I'm going to have -1 at the top and 0 at the bottom. So because I'm getting n over 0, that tells me that this number here is a vertical asymptote. So my vertical asymptote is x is equal to -1. I have no holes. Okay, now we can begin our derivative work. So I have f prime of x. I'll rewrite it just a little bit bigger. 1 minus x over x plus 1 cubed. So what makes it 0? What makes it undefined? A fraction is 0 when the top is 0. So that will give me x is equal to 1. And it's undefined when the bottom is 0, which gives me x is equal to -1. So I have two partition numbers, and out of those two partition number, one is a critical number, the one that's part of the domain. So this one is the critical number. But when I create my sign chart, I use all the partition numbers. So I'm going to pick -2, 0, 2. I'm testing it into f prime, which is what I wrote above. So 1 minus -2 is a positive 3. -2 plus 1 is a negative. Negative cubed is still negative. A positive over a negative is a negative. 1 minus 0 is positive 1. 0 plus 1 cubed is positive, so this will be positive. 1 minus 2 is a -1. 2 plus 1 cubed will be positive, so this is negative. All right, so I'm decreasing, I'm increasing, and then I'm decreasing, which means that you might think that you could say that this is a min, but remember, -1 is only a partition number. It's not part of the domain, so it cannot be a minimum. However, 1 is part of the domain, and because it goes from increase to decrease, it will be a max. And I have to find the y of that. So f of 1 is equal to, remember, I know I've said this multiple times, but it's one of the most common mistakes I see. Anytime you're finding y's, you always have to use the original function. That's where your y's come from. So when I plug in 1 into that, I get a 1 at the top. 1 plus 1 is 2. 2 squared is 4. Okay, so I am increasing one time, one interval, -1 to 1. And I'm decreasing twice, -infinity to 1, union 1 to infinity. And I have a max at 1 comma 1/4. All right, I'm going to do the exact same thing for the second derivative. I'm going to come down here to have a little bit more space. So I have 2 times x minus 2 over x plus 1 to the 4th. And before I go on, let me just double check that. Perfect, okay. All right, so when is it 0? And when is it undefined? So again, it's 0 when 2 times x minus 2 is equal to 0, which gives us only 1x. And it's undefined when x plus 1 is equal to 0, when x is equal to -1. And remember, I don't have to take the 4th because that 4 just tells me that I have x plus 1 4 times. So I don't need to set x plus 1 to 0 4 times. They all give me x is equal to -1. So then I have two partition numbers, -1 and 2. Only one is part of the domain. So now I'm testing in the second derivative, so -2, 0, 3. Okay, so I have a positive 2 in the front. -2 minus 2 is a -4 over -2 plus 1 to the 4th. And because it's to the 4th, then it's always going to be positive in the bottom. So actually, for each of these, I can put a plus in the denominator because it's to the 4th power. So for -2, I have a negative in the top, a positive in the bottom. That's a negative. For 0, I'll have a positive 2 in the front. 0 minus 2 is a negative. So again, that will give me a negative. And 3, I'll have a positive 2, a positive 1. So everything is positive, so that's positive. So I'm concave down, and then I'm concave down, and then I'm concave up. And because 2 is part of the domain, and the concavity changes, this is an inflection point. And -1, the concavity doesn't change, and it's not part of the domain, so it fails both criteria of being an inflection point. So if we write our concavity, because -1 is not part of the domain, you have to write the concave down as 2 separate intervals. If it was part of the domain, you could write it as 1. So I have to split it up. Concave up is 2 to infinity. And my inflection point is 2 comma. All right, I got to go back up here. And I did f of 1, so let's do f of 2 down right below it. So I'm using the highlighted function that's in orange, the original f of x. So I'll have a 2 at the top. 2 plus 1 is 3. 3 squared is 9. So my inflection point is 2 comma 2 ninths. Okay, so good. We have everything. So now it's kind of a tricky part. We got to put everything together. So let's begin by just plotting our points. I can see my y's are really small. So I'm actually going to do my scale of 1 here, and I'm going to put 1/2 right here. And then -1/2 and -1. And then my x's, I need to at least go up to 2. 1, 2, 3. 1, 2, 3. So I'm going to do 0, 0. And then I'm going to have my max at 1 comma 1/4. And I'm going to write max at the top. And I'm going to have my inflection point at 2 comma 2 ninths. And 2 ninths is smaller than 1/2. You could get a decimal version if you just want to double check that. You would see it. So it's about right here. All right, I'm going to do my horizontal asymptote and vertical. So my horizontal is at y equals 0. So that's directly on top of the x-axis. So this is why it's sometimes nice to have different colors to work on it. And then I have a vertical one at -1. X is equal to -1. All right, and then we got to see what's going to happen. So let's look at how we begin. And either you can look at your sign chart. So what I see is that from -infinity to -1, I'm decreasing. And then from -1 to 1, I'm increasing I will hit my max, U-turn, and then decrease again. So because I have the max written there, that's evident that I will need to U-turn. But on the left of the vertical asymptote, I'm decreasing. On the right of it, I increase and decrease. Now the concavity, I'm concave down all the way up to 2. So all of this is concave down except at the vertical asymptote. And then I'm concave up. So on the left of the vertical asymptote, I need to decrease and be concave down. And because of my behavior of my asymptotes, my graph would either have to do this shape or do this shape. But again, I need to be decreasing and concave down, so that has to be the one at the bottom. That's decreasing and concave down. The other one is increasing and concave up, the complete opposite. And then on the right of the vertical asymptote, I need to be increasing concave down, and I need to follow along my vertical asymptote. So I increase, down parabola, I hit my max, I U-turn, still in the down parabola, I hit my inflection point, I change to an up parabola, and I follow along my horizontal asymptote. So sometimes it's nice to write the increase, decrease, the concavity on top and bottom of the graph. That's optional, but if you liked it, that's something you could do in the future.